Ever looked up at the night sky and felt small? Well, get ready to feel even smaller. Today, we're diving into the Cosmic Heavyweight Championship, stars versus black holes. It's a tale of mind-bending sizes, unimaginable masses, and the ultimate cosmic paradox. Let's start with what we know. Stars. Our sun seems huge, right? It's about 1.4 million kilometers across. But in the grand scheme of things, it's just an average Joe. On one end of the scale, you have tiny red dwarfs. Some are only 1/10 the size of our sun, but don't let their small stature fool you. These little guys are the marathon runners of the universe, with lifespans stretching into the trillions of years. Then, you have the giants, the real titans. Supergiants like Betelgeuse are so enormous they make our sun look like a grain of sand. If you swapped our sun with Betelgeuse, its fiery edge would extend beyond the orbit of Mars, swallowing Mercury, Venus, and Earth along the way. That's a star 1,000 times wider than our own. So, stars come in a dazzling variety of sizes, from tiny to truly colossal. But how do they stack up against black holes? This is where things get weird. Black holes are the undisputed champions of density. They come in two main weight classes. First, stellar black holes. These are born from the explosive death of massive stars, usually ones that were at least 20 times more massive than our sun. When such a star goes supernova, its core collapses under its own gravity. Now, here's the mind-blowing part. A star that was millions of kilometers wide collapses into a stellar black hole with an event horizon the point of no return that might only be 60 kilometers across. That's smaller than most major cities. A colossal star, crushed into an object of urban proportions. It's an incredible transformation, a testament to the raw power of gravity. But stellar black holes are just the beginning. The true monsters of the cosmos are supermassive black holes, or SMBHs. These behemoths lurk at the heart of nearly every large galaxy, including our own Milky Way. Our galaxy's central black hole, Sagittarius A star, packs the mass of 4 million suns. That's right, 4 million. And it gets even crazier. The supermassive black hole in the galaxy Messier 87, the first one we ever photographed, has a mass of 6.5 billion suns, 6.5 billion. The sheer scale is almost impossible to comprehend. So, when we ask, how big are black holes compared to stars? We encounter a paradox. Let's take Sagittarius A star again. It has the mass of 4 million suns, but its event horizon is only about 24 million kilometers wide. That sounds big, but it's only about 17 times the diameter of our sun. All that mass is squeezed into a surprisingly compact space. Here's a fun thought experiment. If our sun magically collapsed into a black hole right now, its event horizon would be just 6 kilometers across, about the length of a short city drive. And guess what? Earth would be fine. We'd continue orbiting this tiny dark point just as we orbit the sun today. Why? Because the mass would be the same. A black hole's gravity is powerful, but it's not a cosmic vacuum cleaner. It follows the same rules of gravity as everything else. It's all about density, not indiscriminate destruction. The relationship between stars and black holes is a one-way street. Stars can become black holes, but black holes don't turn back into stars. This transformation is one of the most dramatic events in the universe. For the largest stars, when their nuclear fuel runs out, gravity wins the final battle. The star's core implodes catastrophically. If the core is massive enough, more than about 3 times the mass of our sun, the collapse is unstoppable. It punches through the neutron star stage and forms a singularity, shrouded by an event horizon. A star once spanning 1 billion kilometers is reduced to a black hole just a few dozen kilometers wide. But black holes aren't just cosmic relics. They are active architects of the cosmos. Scientists have found a fascinating link. The mass of a galaxy's central supermassive black hole is directly proportional to the mass of the galaxy's central bulge of stars. It seems these giants are fundamental to how galaxies grow and evolve. They can influence star formation in a cosmic tug-of-war. On one hand, the powerful jets of energy blasting from a supermassive black hole can heat up and blow away gas, preventing new stars from forming. On the other hand, the intense gravitational pressure can sometimes compress gas clouds, triggering a burst of new star birth, and woe to any star that wanders too close. The gravitational pull near a supermassive black hole is so extreme that it can rip a star to shreds in an event called a tidal disruption. The star is stretched and pulled apart into a long, glowing spaghetti-like stream of material, creating a brilliant cosmic light show as it's consumed. A tiny, dense object dictating the fate of entire stars. So, what have we learned on this journey? That size is relative. A stellar black hole can be physically smaller than a supergiant star, but wield an exponentially greater gravitational force. Our understanding of the universe is constantly being pushed to new extremes. The largest known black hole tips the scales at an astonishing 36 billion solar masses. The most incredible part of this story is that we, from our tiny planet, can observe, measure, and begin to understand these cosmic giants. The quest to answer questions like how big are black holes compared to stars reveals a universe more complex and awe-inspiring than we ever imagined. The ultimate answer is that black holes are infinitely denser, dramatically smaller, and monumentally more powerful than the stars that gave them birth. And with every new discovery, the universe proves it still has plenty of secrets waiting to be uncovered. Thanks for joining this cosmic exploration. If you enjoyed this journey into the extreme, make sure to hit that like button and subscribe for more deep dives into the mysteries of our universe. See you next time.